Okay, so I got this question sent to me. P is a point on a given line such that the length of OP, which is the line segment from the origin to P, is a minimum. Find the coordinates of P and this minimum length. So what we're basically trying to say is, we've got this line, right? This 2x plus y minus 10 equals 0. And there's some point on the line that is as close to the origin as is physically possible while still being on the line. Our job is to try and find that point. So in order to get started, a good way to tackle a question like this is just to visualize what you're up against. And the best way to do that is to actually draw this line, and then you can mark a point on it. So if we go through and we quickly work out exactly what this line would look like, we can do that just by getting the x and y intercepts. So to find the x-intercept, all you have to do is make y equal 0, and you would find that x is equal to 5. You can do the same thing to find the y-intercept. You just make x equal 0. And you'll find that y is equal to 10. Now that gives us a way to very briefly draw in a line. Now this line doesn't have to be perfect, but it does help that it's at least reasonably accurate. So we've got this line here, right? And now what we want to say is we want to say that point P is some point on the line, but it is at the point that is closest to the origin. So I'm just going to say that it's probably about there, just for argument's sake. Now I don't know exactly, this could be a little bit off, but I'm going to call this my point P. The point is to be able to visualize what's going on. And I'm going to call its coordinates A and B, just to get us started. Now, what we're eventually going to do is we're going to use the distance formula to find the distance between 2 points. If we've got this origin as the point 0, 0, and the point P has coordinates A and B, then we can use the distance formula to try and find the distance between the 2 points. After that, we can work on trying to make that as small as possible, but for now we just need to know what we're up against. So the distance formula, you would have seen it before, is equal to the square root of the difference between the x-coordinates squared plus the difference between the y-coordinates squared. Now, plugging in our values that we've got so far, that would mean that our distance is equal to the square root of 0 minus a squared plus 0 minus b squared, which if we shrink it down is actually just the square root of a squared plus b squared. Now this looks a lot like Pythagoras theorem, and that's because it's actually based off that. So you'll notice the similarities. Now we can't do much with that at the moment, especially because we've got two different letters. We've got an A and we've got a B. The trick here that is the hardest part is we have to manipulate that B so that it uses an A variable instead. Now we can do that because we know for a fact that the point P definitely lies on this line, which actually makes it a little bit easier because it means that if it lies on that line, it has to follow the line's rule. So what we need to do now is we're going to sub our A and our B into the equation. And then we're going to find an expression for B in terms of A. Now all I have to do here is move the 10 and the 2A over to the other side, and I would find that B is equal to 10 minus 2A. Now the beautiful part about that is, once I've done that, I can actually change the coordinates of point P to match that. More importantly, I can change the coordinates in here. So if I take this down, and I will now rewrite the problem, but instead of writing B squared, I'm going to use the equation that was given to us. So we've got our A squared from the first part, but we've also got 10 minus 2A squared. And the whole lot is under a square root symbol. That is the expression for any point on that line and its distance from the origin. That will find the x-coordinate, because our x-coordinate was A. Now the idea here is we want that to be as low as possible, and in order to do that we actually need to use the derivative. So we need to differentiate this, let it equal 0, which will help us find the minimum. Now if you're a little bit fresh with this kind of stuff, I suggest you go back and have a look at the calculus tools and the applications of differentiation, because this stuff's covered in length in that section. But basically what we're going to do is we're going to find the derivative of the distance with respect to A, and we're going to let that equal 0. And when we do that, if we solve for A, it will give us the x-coordinate of our point P. Once we've done that, we just need to sub in the last bit and we can find the y-coordinate of point P. So finding the derivative of a problem like this is a little bit tricky. In fact, it's probably not something we can tackle right now until we expand and simplify inside the brackets. So if we take that third and we just expand it a little bit, we'd have A squared plus 100 minus 40a plus 4a squared, the whole lot under a square root symbol, which when we simplify it is the square root of 5a squared minus 40a plus 100. Okay. Now we differentiate that. In order to differentiate it, you need to use the chain rule, which is covered in calculus tools. So in order to, if this is the distance, in order to find the derivative of the distance, we have to let u equal the inside piece differentiate that, and then use that along with the original problem to find the derivative. Now the chain rule is covered extensively in Module 5, which is calculus tools, so I'm not going to go over the nitty-gritty stuff, but once you're done, you'll be able to find your derivative in terms of a. Minus 40a plus 100. Okay, so that's the derivative of our distance. Now we can shrink that down as much as we possibly can because we actually want that to equal 0 in order to find our minimum. Now, trick with fractions. If you've got a fraction that equals 0, that actually simplifies to just the numerator equaling 0. So we'll have 10a minus 40 equals 0, which will give you a value of a that's equal to 4. Plug that all the way back into your original problem, or even just straight into here, because this is a quick little formula to find b, and you'll find that b is equal to 10 minus 2 times 4, which is 2, once you simplify it down, and the point P will now have coordinates of 4 and 2. Finally, when you want to find the actual distance, we're going to take this formula, which was the simplified formula for distance, sub the numbers 4 and 2 into that, and we'll find that the distance is equal to the square root of 4 squared plus 2 squared, which is the square root of 20. And that is the lowest possible distance. Now I know that because I used the distance formula and then I used the derivative in order to find a minimum. Now this is a pretty intensive question. It's unexpected that you'd be able to see this before you fully tackled the chain rule and you fully tackled differentiation. So with those tools under your belt, this question becomes quite straightforward, but early on in the year you find this question you might struggle quite a substantial amount.